we were looking at the back propagation, and these are the 7 steps to be followed in any of the back propagation algorithm to train a neural network. All right. Now let's go for an example of the error back propagation. Right? So this is the example of error back propagation. So we'll try to solve the same problem which the single layered neural network failed to classify, because we just want to display the capabilities of a multi-layered neural network, right? So I should be able to solve the same problem which the uh, single layered neural network failed to classify. Okay, right, let's go for the same this thing. So let the data be as follows. So right, the class 1, or let me go for, say, class 0. The input data is like this: 0 0 1 0, and this is 1 1 0. This is for class 0, and let's write for class 1. This is actually the XOR problem if you look carefully, right? This is 0 1 1 1 and 1 0 1 1. So as we know now, in this kind of representation, the last bit represents which class it is. All right, okay. So this is our objective. Now let's try to define the neural network which we are going to consider for the solution of this problem. Since the output is either 0 or 1, we can say that the number of output neurons should be just 1, because I just have to classify whether the input output is 1 or 0. Right, so we can say that the neural network which we are going to consider now has 3 input nodes, okay, and 1 output node. So let us denote. So where is the input node? There are 3 input nodes like this. Okay, this is input, and you can see that there is only 1 output node, that is here, and there is 1 hidden layer, and the hidden layer basically has 4 nodes. Okay, so this is the input, this is the hidden layer, and this is the output layer. This is what we are going to consider. Okay, and let us use the same sigmoid function for the activation of the hidden layers and the output layer. Okay, so again, we have the options to implement the SGD technique or the batch training technique, or right, whichever we prefer. All right, so let's try to stick to the most simpler and the intuitive method, right, for the training purpose, right? So that is we stick to the SGD technique itself and implement this. All right, so let's try to write a MATLAB code for this. Okay, so let's go to the MATLAB screen and let us try to write a code. Okay, right. All right, I will open up a new, what you call, text editor. So edit, and let me give a name called as the back propagation XOR problem. All right, so anyway, that is not there in my list of programs. Okay, so I can ask for edit and it will open up that particular this. Okay, so this is a function. I'm writing a function here. Okay, so the outputs, let's define. So I have two outputs. So one is the W1 and the second output is W2, right? W1 and W2 are the weights, should be equal to give the same name as your function. Okay, so that is, okay, its name is changed. Okay, I'll just PRPO, I'll just close this, okay, because I don't want to have a different name. I'll just delete that. I'll do it once again. Okay, edit OP. All right, let's say this is the one. So I'll define W1 and W2. These are the outputs is equal to give the function name. Back propagation XOR, and just give the inputs that you are going to pass. What are the inputs you are going to give? The W1 of the first one, W2, the second, weight, the input vector, and the desired. Okay, compare this with the previous one. So, oh, I have to mention a function. Sorry, my mistake. So just this is the format, right? So function is equal to this. Okay. All right. Then, so by default, you need to define alpha value, make it 0.85. Fine. Then define the number of inputs, that is n is equal to 4. Okay. Then for, right, let's define the variable, say I is equal to 1 to n, all the four, until all the four inputs are repeated. Right, I have to say x, take the x is equal to capital X of, this is what we did earlier, right? So ith row and all the columns. Okay, similarly do this for the d. So d is equal to d of ith desired output, desired output decay. Then calculate the v1, right? So v1 is equal to the w1 into x, correct? Then what you did, then you calculated the y1 is equal to sigmoid function. So I think we named it as my sigmoid. My sigmoid of the v1. So calculate that, then calculate a v. So how do you calculate a v? V is equal to the weight w2 into, now it is not x, it is y1, correct? Because y1 is what you are using to update your to calculate the final output. So final output y should be equal to the my sigmoid of v itself. Are you okay? So you could calculate the y and v so far. Right. Now use this to calculate the error. So error E is equal to d minus y, isn't it? D minus y. So once you perform d minus y, calculate the delta. So delta is equal to, how do you calculate the y? I have to multiply, so it's element by element. So dot into 1 minus y. Is it that? Sorry, into multiplied by e. Sorry, there is an error vector. So dot star e. That's a delta. right? Using this delta, calculate E1, right? The one layer before that. That's why E1 is equal to, right, W2 transpose. Just remember the step. It has to be a transpose, correct? So W2 transpose into what? W2 transpose into delta. So use this E1 to calculate the delta 1, right? Delta 1. So what is delta 1? Right? Can you tell me the equation for delta 1? Delta 1 has to be the phi of y1 dash, right? So how do you write that? The phi means it is phi of y1 dash means it is y1, right? Dot star 1 minus y1, right? Dot, write the error. So the error here is E1. Okay, same notation I'm trying to follow, right? What we followed in the theory part, right? So that it becomes easy for you. Then once I calculate E and E1 and delta and delta 1, I'm supposed to update the weights now, correct? So how the weight updation happens here? Straightforward. So calculate dW1. dW1 is equal to, right? How do you calculate dW1? The alpha, the into delta 1 into the input, that is x, right? Take a transpose. This is dW1 and update. So W1 is equal to the weight W1 plus dW1. That's how you update the first weight. Similarly, go for the second weight, right? So that is dW2, dW, 2 has to be equal to, apply the same rule. Okay, that is alpha into delta 2 into, see what you are multiplying now, you are not going to multiply x dash, you are going to multiply with y1 dash. Okay, use this to update the weight too. So W2 is equal to W2 plus dW2. Okay, so we updated both the weights, we got our output. So I should finish. So end, this is the end for that, and I need another end over here. Okay, so for the function. So right, you can see that in this code we are it takes the point from the training data set, right, calculates the weight update. So you take x as your training data, one of the training data, d is the desired part of that. All right, so the process is very identical to our previous case. uh, okay, let's try to okay, I think we need a modification in the delta function. That is because the what we are multiplying is a complete vector, so this v becomes a vector now instead of single value. Anyway, I'll show you that later when we run the code. It's going to throw up an error, and we'll rectify that there itself. Okay, all right. So for the time being, let's close some of the unwanted windows. Okay, now let me try to write the function, right, which actually tests this code. Okay, so I'll just try to run. Okay, I'll just try to edit that code. So this is to test PROPXR. Okay, I'll write in new code to give the inputs now. All right, so right now if you remember, our first step has to be giving the inputs, defining what are our inputs, right? So let's define the inputs now. So if you remember, the input has to be denoted as x is equal to, first I'll give 0, 0, 1, then I'm going to give 0, 1, 1, next I'm going to give 1, 1, 1, then I'm going to give 1, 0, all the four uh, weights have been given. Now let's define the d. Okay, d is equal to, first one 0, 0, so it has to be 0, then 1, next one is 1, 1, that's also 0, then 1, 0, which is going to be the 1 in the output. Okay, so we defined this. Now let us initialize the weight vectors. Okay, how many weights we need? We need two vectors. So this is w1 is equal to, right, look at the size now. So I'll write, say, 3.5 into RAND, random. Look at the size of your what you call as the hidden layer. There are 4 neurons, right, and 3 inputs. So it has to be 4, 3, right? 3 inputs, 4 such neurons, right? So that's the size I have to define, minus 2.5, maybe. Anything you can make right here so that it becomes a random. All right, so W2, the second one, I'll define using a different way. Say 2.5 into, now look at the size. It's a different size. The second layer has only 1 neuron, right? And how many inputs will come to that? 4 inputs, because output of my previous layer is connected to this layer. Output previous layer is a hidden layer which has 4 neurons. They will generate 4 outputs. All the 4 outputs will be connected to this neuron. So there is 1 neuron, 4 inputs. All right, so the size has to be 1, 4. So just it takes some time for you to get adjusted to this, right? But then it will be fine. All right, so minus 1. Okay, let me define the weights in this fashion. Once it is done, now let us define the epoch. All right, so I'll define, say, for the epoch number, epoch is equal to 1 to 100. What I'm going to do, I simply call my function. So that is W1, W2 should be equal to, call the function. Function has a name, backdrop XOR. Pass the values W1, W2, X, and D. Okay, finish, and I don't have to do anything over here. Okay, that is done. Now what you do, you do the testing part, right? So let's go for the testing part of this. So how do you do the testing? You have to define the number of classes. N is equal to 4. Then what we can do, we can simply write a for loop for, say, j is equal to 1 to n, right? Define the x now. So x is equal to capital X of the j, comma, all the columns, transpose. Okay, then I need to from the x, give it as input and calculate v1 first. So the v1 becomes equal to, if you remember, the first weight into x, right? So this is w1 into x. Okay, then once w into x is done, I have to perform the sigmoid function. So this is y1, the partial output is equal to my sigmoid of which one? V1. All right, so I do calculate the V1 and I calculate Y1. Once I have Y1, My next objective is to calculate the partial output of this output stage, that is V. V is nothing but W2 into its previous input, the output of the previous stage, that is Y1. Okay, use that. So once you have this V, you can calculate a final output Y. So how do you do that? So Y is equal to my sigmoid of V itself. Okay, once this Y is done, okay, let me put it in the form of an array, Y of J. Okay, so that I can simply display the Y at the end. Okay, so okay, first let me close the loop itself, so that is end. Then I want to display the Y. Okay, now actually I'm expecting an error when I run the call. When I run the code, I'm expecting error in the this one, my sigmoid function, because there we had defined only for single variable, not a vector, right? So that's one change that we are expecting. Anyway, let me run that and let me correct that later. So I'll show you what exactly is happening. So you see, right, line number 15. So line number 15 is this. Sorry, it's a different error. Let me check that once. Okay, it's a dot star. So okay, let me make some corrections. Okay, let's see now. Let's try to run this code. V1 W1. Okay, it says you have to put a dot because it's a vector, but as of now this is a okay. I don't think this is a dot star because W1 has a size of 4 into 3. Okay, let's check. Maybe it will show another error in that case. See, yeah, in my sigmoid. So this is what I was expecting actually, but so this has to be, see, it is actually working for only single element. One, now I make it as element by doing a dot star. Okay, so I simply converted the value of what you call Y is equal to 1 dot divided by 1 plus exponential of minus x. Okay, so that's what trying to do here. All right, so let me save this. Okay, let's come back. I think this should run now. No, let me just check. dw2 is equal to, okay, no delta 2, sorry, it's just delta 1 itself, because we are not calculating the other delta, right? One is delta 1, so should be using only that. Okay, let's check, because indicates y of Okay, let's just come back. Let's see this, what happens. Let's see that later, because I think y is in a different size now than it is expected. Okay, let's see. Okay, not learning. Let us increase. 0.5, 1,000, 10,000. Just a second, it's not learning. Let's see, just this. Let's try to trace what is the mistake. Okay, theory part we are very fine, but right, the practical implementation is giving me some error. It's not learning. Let me check the code once again. Okay, let's come back from the beginning. So this is the back propagation code, right? This is the function. So in the function, you can see that we define the function backprop XOR W1, W2, X and D, learning alpha, n is equal to 4. For I is equal to 1 to n, define X, define D, define V1 to into W1 into X. I still have it down. Okay, let's see what is W1. Let's just open. So this is W1 is 4 into 3. W1 has, no, it should be W into X only, right? So just see, W has 3 values. I can multiply with the 3 elements over here, right? So first one into first, second is into, but it was saying that it is an error, right? So I think that's the reason why it's not. Let me just check that once. So I'll come back to this. I'll change this to simply W1 into X. It's obvious because my X is, you can see here, X is simply 3. So W into X should work, I guess. Okay, let me just check once again if there is any. Okay, this is a dash missing. Okay, now let us try. All right, so let's go back. I'll come with the smaller number, say 100. All right, let me calculate the same thing. I'll increase this. Okay, let's see. Now it's actually all the 4 values are different, so it means it is learning something. It cannot be, all the values cannot become same, that's all. Let's try. Okay, 4, 9 and 5, 0. Let me increase further. Oh, it's tending to be same. Then that is not going to work. If all of them becomes, yeah, now you see 1. Okay, let's go further. It's learning. There is something that is happening. You can see all of them are different, right? If it's not becoming same, it is, right, becoming different. Now let us see what's going to happen. We are expecting all the 4 values to be different. Okay, it's 1 1 1 and this thing again, this is not going to work if it is like this. But again, this is not a convincing result. Let's check. I think we have done some other logical mistakes. Let's see. Okay, so one we corrected now, so let's move further. After that, after this value, y x is defined, d is defined, v1 is w1 into x, y1 is my sigmoid function for v1. Calculate a v which is w2 into y1. That's correct. So use this to calculate a y value. That's also right. Calculate error d minus y. Delta is equal to y into 1 minus y into error. Calculate error 1, which is nothing but w2 transpose into the delta value. Calculate a delta 1, which is y1 into 1 minus y1 into e1. So this looks fine. Then my job is to calculate a dw1, which is alpha into delta 1 into x. Okay, w1 is w1 plus dw1. That also looks fine. dw2 is equal to alpha into delta. Okay, this is a mistake, sorry, this is just delta, sorry, because I calculated delta but I never used it, right? For dw2 it has to be delta, sorry. Right. Okay, now I think I will get that, because I was using the same delta 1, right, for updation of both w1 and w2, right? Weight updation is not proper. Okay, looks like we found what was my mistake, right? Let's go ahead. Let's try this now. Again, I'll start from this small number. I don't want to waste the iterations. Okay, so I'm expecting this to come within 1000 or something like that. Okay, now I can actually put this y of j. That was my mistake. So y of j is equal to this, and then I print. Okay, you can see y is like this. Okay, y is completely different. This is what was expected. And okay, I'll run. Now you see, right? We are coming closer. You see, we are expecting 0 1 0 1, right? You can see that 0 0.03 0 0.93 0 0.5 0 0.95. Let's go further. 10,000. I'm expecting more clear results now. You see, 0 0 0.9 0 0.01 0 0.99. So one more 0, you will get appropriate. Okay, 0 0.00 0 0.49 0. Okay, this may not be fine. Okay, because of the random numbers we got. Let me run the same one thing. Okay, now you can see 0 1 0 1, very close, right? So 0 instead of 1. Okay, let's increase this by one more. All right, so you can see that the result is pretty much closer, right? So we expected 0 1 0 1 as output, and it's coming very close, right? Okay, so like this, now you can see that if we use a multiple layers, right, in the multiple hidden layers in our neural network, it is capable of performing what is called as the weight updation according to the error back propagation, because of which you will be able to solve the multiple what you call a problem which has non-linear classification, right? So single layer was not able to do that, but this multiple layer hidden layers or multiple layer neural network is capable of doing this, right? Now, is there any technique which using which we can improve this performance, right? So can we so in the single layer you saw that there is what is called as SGD, batch, mini batch, etc. We did something like that, and we could, right, compare the results like in terms of what you call the error, right? So the learning rate was different for each one of them, and you saw that there is a difference. We actually had a plot, right, of the performance measure of those kinds of training in case of the single layer neural network, right? Very similar to that, we are going to have the comparison of various techniques here, for which we need to introduce few more newer terms, right? So SGD is already implemented. Now we see the result here. Definitely batch and mini batch can be done, but in addition to that, we can go one step ahead and bring the term called momentum, right? So that momentum will help us in improvising the results, right? And get a result in a quicker fashion, because in this case you can see that there are a lot of weights to be updated, right? So as you increase the number of number of hidden layers and the number of neurons in each of the hidden layer, neural network is going to take more time, right? It's going to take more and more time for right, what you call as the learning, right? So because of that reason, we have to bring some changes in the algorithm. So for that reason, we will be bringing up what is called as the momentum. There is a term called momentum. So in the next class, we will see what is a momentum and how to use this momentum for in case of a training of a multi-layered neural network.